Hello, everyone. Welcome again to another video series on PyTorch. Today, we are going to be talking about PyTorch and neural networks. And before I begin, I just wanted to mention a little bit of where we are and where we are going. We have been working on theory, trying to go through different definitions of PyTorch, when and how to use PyTorch, and things like that. And after this, what we will do is that we'll be able to embrace the future of learning. And by that, I mean we will be able to use Chat GPT and also use Google Colab together. And that way we can be able to see the anatomy of a neural network and also the different aspects of the neural networks and how they work. And we will be able to accomplish that, I think, very easily by trying to utilize ChatGPT and also utilize Google Colabs. So we'll be going to Google Colab. If you're not aware of Google Colab, I did briefly introduce it during my previous video on NumPy, and it's pretty much just an IDE, but it's also more than an IDE because it provides GPU. And as you will be able to see a little bit later on, we need GPU to be able to run and also train these neural networks. Our machines, our laptops and desktop computers that we use primarily run on CPU, but CPU is not effective and it's not fast enough in training these neural networks, and that's why we need a GPU. And we can get that GPU from Google Colab. There's a free version where you just go there, you put in your username or you put in your email address if you have Gmail, or you can also register and you can run the free version. And if you want to use more GPUs, then you can be able to get the paid plan. And I do have a paid plan with Google Colab. And for me, it costs me around $20 a month. And I think that's reasonable. I also find it to be very helpful, especially once you start learning more about neural networks and training the neural networks. You'll find that you may need a little bit more GPU than what is allocated in the free version of the Google Colab. And it may not be a bad idea to consider maybe trying to maybe purchase, which, as I said, it normally costs about $20 a month. And then you can continue with learning more on machine learning and deep learning. Without much ado, then, we'll go ahead and start talking about PyTorch and neural networks. And I am gonna talk about, this is just a typical basic architecture of a neural network, essentially. And neural network, normally we have an input layer, and then it's just layers. We have an input layer, we have an hidden layer, then we have an output layer. Input layer, hidden layer, then output layer. We can have one hidden layer as we have in this one, or we can have two, we can have three, we can have four, we can have five, we can have six, and all that. And these are neurons. These are neuron, and this shows you how information moves. It can move from this neuron, can go there, can go there, can go there, can go there, and all the way down there. And also from this neuron, it can go there, 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 like that. and information goes this way. For some neural networks, it goes this way. For some other neural networks, especially when you have a lot of hidden layers, information can also go back and forth, back and forth, back and forth, the different layers. And so that's a little bit of a basic architecture of a neural network. In PyTorch, we have different neural networks, and I'll just touch a little bit on this very, very briefly, just so at least you know. But we do have different neural networks that we can use in PyTorch. We have the convolutional neural networks, which we also called CNNs. Then we have the recurrent neural networks, which are also called RNNs. Then we have the transformer networks, the generative adversarial networks, which are also called GNNs. Then we have the autoencoders. We have the feed-forward neural networks, also called FNNs. And then we have the capsule networks. I'll just touch each as we go very briefly. We have the convolutional neural networks, or the CNNs, and these are used primarily for image processing, classifications, and other vision tasks. And example architectures in PyTorch include the ResNet, VGG, and the AlexNet. And applications of convolutional neural networks, as we said, include image classification, and they help with identifying the category of an image from a fixed set of categories. They're also used in object detection and for identifying objects in an image and drawing bounding boxes around them. And convolutional neural networks are also used in segmentation. That's dividing an image into segments to locate and classify objects at a pixel level. And convolutional neural networks are a class of deep neural networks that are particularly powerful for tasks involving images. They are designed to automatically and adaptively learn spatial hierarchies of features from low-level edges and textures to high-level objects through layers of processing, through layers, convolutional layers, through layers of processing. And in PyTorch, CNNs can be implemented using the torch.nn module. And this torch.nn, NN stands for neural network, torch.neural network module. This module is one that we are going to see a lot when we start training and building and training our neural networks. But in PyTorch, CNNs can be implemented using the torch.nn module, which provides all the necessary components such as convolutional layers, that's the conv2D, pooling layers, that's we can have the max pool 2D, and we'll see this once we start building and training the neural network. And also fully connected layers, like linear layers, fully connected layers. And using these building blocks, one can customize and build powerful CNN architecture tailored for specific tasks. And a good example of CNNs, just an example actually that I just got from Google. I Googled an image of CNN, convolutional neural networks, and I got this. But it shows that we have an image here that we are the input that we are trying to figure out. We're trying to feed it through the network and see if the network can be able to learn the patterns in this image and identify this as a number 2. So essentially we start with the data, and our data here is an image of number 2, but This data can be thousands and thousands and thousands or even millions of images. And say that you have thousands of images with number 1 to 10, and you want the neural network to be able to identify this is an handwritten number 2, and you want the neural network to be able to identify what number is written there, and you have like millions of them, and you feed it through the neural network, and the neural network, you want it to be able to identify the correct number. And so what you do is that essentially you train the neural network first. So you give it a bunch of these numbers, you know, like handwritten numbers from 1 to 10 or 1 to 9. And with that data that you have, you divide the data into training data and testing data. And we'll see this as we continue. But you divide the data into training data and testing data. Sometimes you can say 80% of the images are going to be of training data and 20% are going to be of testing. So you train your neural network with all the 80% of those millions of images, and the neural network learns different patterns in those numbers. And when you are training the neural network, because this is supervised learning, what you do is that you give the neural network the data, the input data, and also you give it the labels for the training. And you can see this 2 is number 2. 3, if it's handwritten 3 is number 3. So you have a lot of that information, you feed it that. And then once you train the neural network, then you can now try to see if you can make some predictions. So you take your testing data and you give the neural network the testing data with just the images but without the labels. So you don't tell it, for instance, this is 2. You just give it this and you let it tell you what it thinks of this. So this is where you run through this, and then the neural network is gonna try to figure out what this number is, and then it's gonna tell you like maybe it's a 2, and it gets it right. Or it may tell you that this is a 7 and it gets it wrong. And you can tell that it's getting wrong because you do have the labels for the test data. So you know, although you haven't shown the computer the labels for the testing data, but you know that this is a 2, and you want the computer to try to see whether it's going to get it right. So it's going to make the predictions. And this is just a simple neural network for convolutional neural network. You can see we have the conv2D convolution. And we have kernels. We'll talk about kernels, and also we'll talk about max pooling. And we saw that these convolutional neural networks, they have fully connected layers. And so we'll see this much in practice as we continue with our PyTorch journey. But for now, I just wanted to introduce you to different neural networks that we can work in PyTorch with. And one of that is convolutional neural networks that, as we said, is used when you're working with images. And so we go to the next one. And the next neural network that we can use in PyTorch is recurrent neural networks. Recurrent neural networks, or RNNs. And these are ideal for sequence prediction problems, such as time series analysis or natural language processing or natural language processing. And they include implementation of RNN, LSTM or long short-term memory, and also GRU or gated recurrent unit, gated recurrent unit. And applications for recurrent neural networks include language modeling, and text and text generation, like generating text by predicting the next word in a sentence given the previous words. Another application for recurrent neural networks would be in speech recognition, and this would be converting spoken language into text by analyzing the temporal dependencies in the audio signals. And in time series prediction, we can also use recurrent neural networks. And time series prediction is forecasting future values in a series of useful in a series. So time series prediction is forecasting future values in a series, and this is useful in finance or weather modeling and etc. And then recurrent neural networks can also be used in machine translation, and this is translating text or speech from one language to another. And also recurrent neural networks can also be used in video analysis, and that's understanding and predicting sequence in videos such as action recognition. Recurrent neural networks are a class of neural networks that are particularly well suited for processing sequential data, as we have said. They are powerful for modeling time series data, natural language, audio, and any other type of data where temporal dynamics are important. And in PyTorch, recurrent neural networks can be implemented using the torch.nn module, as we have seen with the convolutional neural networks. So in PyTorch, recurrent neural networks can be implemented using the torch.nn module, which includes RNN, LSTM, that is the long short memory, and also the GRU, and that's for the gated recurrent unit classes. So there are those classes, and in the torch.nn module, which we can utilize to in PyTorch. And PyTorch simplifies the management of hidden states and allows for dynamic computation graphs that can handle varying lengths of input data, which is essential for batch processing of variable length sequences. We'll see about batches in PyTorch, and we will also see why we need them, but we'll discuss that as we continue with our PyTorch series. So overall, recurrent neural networks are fundamental for understanding and processing sequences, offering robust frameworks for tackling complex problems across a variety of domains where context and history significantly impact the output. And a very just a decent example of a recurrent neural network, basic example of a recurrent neural network. You can see it's like this, and we have input layer here, then we have one hidden layer, then we have another hidden layer, then we have an input layer. And in this neural network, information flows this way. It can also flow backwards, recurrent. It flows back and forth. It can flow back and forth. And that's just a basic architecture, of a recurrent neural network. Information can flow this way or that way, this way, back and forth. And we have the input layer, We have an hidden layer, another hidden layer. This has two hidden layers. You can have a lot of hidden layers, as many as you want. You can have 10, 12, 15, 13, 20. So you can have any number of hidden layers within your neural network. And next, we'll talk about the transformer networks. And the transformer networks are known for their effectiveness in handling sequential data, surpassing the recurrent neural networks in many tasks, especially in natural language processing. And the transformer model is available through the torch.nn.transformer. Remember the torch.nn module. So the torch.nn.transformer, that's how we can be able to access the transformer network model. And pre-trained versions like BERT or BART are accessible via libraries like Transformers by Hugging Face. I don't know that you know about Hugging Face, but we'll probably look at it a little bit further. But this offers different, offers models, data sets for machine learning, and it's just holds a lot of information that is important for different neural networks, and also for understanding machine learning and deep learning. Applications for transformer networks include, as we have said, natural language processing, where tasks such as translation, summarization, and sentiment analysis. So natural language processing involves tasks like text translation, summarization, and sentiment analysis. Transformers are the backbone models of the BERT, as we have said, GPT, and T5, which have set new standards in natural language processing tasks. Transformer networks can also be used in image processing, and transformers have been adopted for image recognition tasks, leading to modules like Vision Transformer that achieve state-of-the-art results in classification tasks. And also, transformer networks can also be used in time series forecasting, leveraging the ability of transformers to handle sequential data for predicting future values in series. And also, transformer networks can also be used in music generation, where you can use them to generate music by modeling sequences of musical notes and their relationships. So essentially, transformer networks have revolutionized the field of natural language processing, and have increasingly been adopted across various other domains like image recognition and time series analysis. The transformer model, which was introduced in the seminal paper, Attention is All You Need, is distinct for its reliance on self-attention mechanisms, achieving the recurrence mechanism used in traditional eschewing the recurrence mechanism used in traditional recurrent neural networks. I'll say that again. The transformer model, which was introduced in the seminal paper, Attention is All You Need, is distinct for its reliance on self-attention mechanisms, eschewing the recurrence mechanism used in traditional recurrent neural networks. So in PyTorch, the transformer model can be built using the torch.nn.transformers module, which provides high-level API based on the original transformer architecture. PyTorch also includes hyperclasses like torch.nn.transformer encoder and also torch.nn.transformer decoder to facilitate the construction of just the encoder or the decoder. And transformers offer significant advantages in parallelization, scalability, and effectiveness, particularly in tasks where long-term dependencies are crucial. This has led to their widespread adoption and continual development in various fields beyond natural language processing. So transformer networks, a very good example that I saw. I found this online on Google, transformer networks, and you can see this encoding and decoding and inputs, and then the process, and then they go to multi-head attention and output probabilities. We have so you can see here the basic architecture of a transformer neural network. I wasn't going to go deep on this. I just wanted to introduce you to the different neural networks that you can be able to utilize with PyTorch. So we'll go to the next one here. And the next one that we're going to be talking about is going to be the generative adversarial networks, or GANs. And these are used for generative tasks such as creating new images that mimic the style of a given data set. And PyTorch provides the basic building blocks for creating discriminators and generators, often customized by the user. We'll see this in a minute. Applications for generative adversarial networks include image synthesis, generating new images that mimic the style of a given data set, such as artwork or photos of faces. And generative adversarial networks can also be used in super resolution, that is enhancing the resolution of images. It can also be used in style transfer, and that is applying the style of one image to the content of another, such as turning a daytime photo into a nighttime photo. And generative adversarial networks can also be used in data augmentation, and that is generating new training data for machine learning models. And also they can be used with anomaly detection, and that's detecting unusual patterns or outliers in data. Generative adversarial networks are a groundbreaking and popular class of neural network architecture used primarily for generative modeling. Generative adversarial networks consist of two neural networks that are trained simultaneously in a computing setting. Important. Generative adversarial networks consist of two neural networks that are trained simultaneously in a competitive setting. These two models are the generator and the discriminator, and their adversarial training gives rise to the name generative adversarial neural networks. Generative adversarial networks. They are the two models of the generator are the generator and the discriminator. Generator and discriminator. And their adversarial training gives rise to the name generative adversarial network. So GANS, the generative adversarial network, consists of two neural networks that are trained simultaneously in a competitive setting. So that's an important thing to note. And implementing generative adversarial networks in PyTorch involves defining the architecture of both the generator and the discriminator, typically using models from torch.nn again. Training a generative adversarial network in PyTorch requires careful management of the training loop to ensure that neither the generator nor the discriminator becomes too powerful too quickly. And generative adversarial networks represent a powerful tool for generative tasks, but they require careful tuning of hyperparameters. Those are the parameters that we'll talk about this, but these are the parameters that you create yourself, and training dynamics to achieve the best results. Their ability to generate new high quality data from learned distributions continues to drive research and applications across various fields. And this is a basic example I got from online of generative adversarial networks, or GANs. And we have the training set, and we have some noise, and we have the generator here. We have a fake image, we have a discriminator, and then it can decide real or fake. So, but that's just a little bit of just an illustration of a basic generative adversarial network. Just wanted you to have an idea. We will we'll move on to the next slide, and another network, neural network that we can be able to utilize in PyTorch is the autoencoders. And the autoencoders are used for unsupervised. See, the other ones that we're working with is more for supervised learning. Now this one is for unsupervised learning tasks such as dimensionality reduction and also feature learning. Remember, in unsupervised learning is whereby you give the computer, and the computer tries to deduce the patterns, and then it can be able to maybe tell you, it can put the dogs together because of the patterns that it learns. We don't have any labels in unsupervised learning, so the computer learns the different patterns by itself, and then it can be able to classify dogs. It can put the dogs in the dogs place, it can put the cats in the cats place, cows in the cows place, things like that. So we don't have labels, there's no label data. It's more about the computer trying to learn patterns, and from those patterns it can be able to group items or objects together. And also autoencoders, variants like variational autoencoder or VAEs are also popular for generative tasks. But these ones, remember, we use them for unsupervised learning tasks. Applications for autoencoders include dimension reduction, similar to PCA. Autoencoders can deduce the dimensionality of data, which is useful for visualization. Example, using 2D or 3D plots, and to improve the efficiency of other learning tasks. Autoencoders can also be applied for feature learning. Autoencoders can learn useful features automatically from data. And this is what we are trying to say, which can be used for tasks such as classification, when we are classifying the cats and the dogs, and the cows, or anomaly detection. So in unsupervised learning. Autoencoders can also be used for anomaly detection by learning to reproduce only the common patterns in data. Autoencoders can be used to detect outliers or anomalies, which will have higher reconstruction errors. And it just makes a lot of sense because they learn to reproduce only the common patterns in the data, and that's how they function, where you can be able to reproduce the patterns in a cat and it can classify the cat, reproduce the patterns in a dog, and then it can kind of classify it in the dog category, things like that. So if there's any anomaly, then it can be able, because it's learned those patterns, then it can be able to see the anomaly, and it can be used in that way to be able to detect an anomaly. And also autoencoders can also be used in data denoising, and autoencoders can be effective in removing noise from data, as demonstrated by denoising autoencoders. And also autoencoders can also be used for data generation and imputation. Variational autoencoders, in particular, are used for generating new data samples and for imputing missing values in data by learning the distribution of the input data. And so, essentially, autoencoders are a type of neural network used for unsupervised learning of efficient codings of unlabeled data. Unsupervised learning and labeled data. Unsupervised learning and labeled data. The aim of the autoencoder is to learn a representation or encoding for a set of data, typically for the purpose of dimensionality reduction or feature learning, running the different features in an object or an image. Implementing autoencoders in PyTorch involves defining the encoder and decoder structures with using the torch.nn module. See, this is the module that we keep on seeing recurring as we go through our neural networks. The torch.nn, the NN is for neural networks module. Training involves computing the reconstruction laws and using an optimizer. We'll see what an optimizer is as we continue to minimize these laws. And essentially the goal of deep learning is try to minimize the loss. And autoencoders can be straightforward to implement, but require careful tuning of the architecture and training parameters to ensure good performance, particularly for complex data sets. Example of autoencoder I just got from Google is this, and we have the input image, latent space representation bottleneck. This is the encoder, the input image, that section, encoder. Then we have the bottleneck, and then we also have the reconstructed image and decoder. So pretty much just a basic illustration of the architecture of an autoencoder neural network. Then we go next to the feed-forward neural networks, or FNNs. And the feed-forward neural networks are the simplest type of artificial neural network, and they consist of input, hidden layer, and output layers. I'll say that again. They are the simplest type of artificial neural networks, and they consist of input, hidden, and output layers, where connections between the nodes do not form a circle. Typically implemented using the torch.nn.linear, linear like a line, linear layers stacked together. Applications for feed-forward neural networks, they can be used for classification, and in that they can be used for categorizing image inputs into predefined classes. Applications include image classification, sentiment analysis, and more. They can also be used for regression, and this means that they can be used for predicting a continuous value attribute, a continuous valued attribute associated with an object, common in forecasting sales, real estate prices, etc. They can also be used for pattern recognition, for recognizing patterns and irregularities in data, used in character recognition and biometric identification, etc. And they can also be used for function approximation, that is, approximating complex functions useful in control systems, robotics, and other engineering applications. The feed-forward neural networks, also known simply as feed-forward networks, are the simplest type of artificial neural network architecture. In a feed-forward network, information moves in only one direction, forward, and feed forward, feed forward. Information moves forward in one direction, forward from the input nodes through the hidden nodes, if any, and to the output nodes. There are no circles or loops in the network, hence the term feed forward. Implementing a feed-forward neural network in PyTorch involves defining a model class that inherits from the torch.nn module. This class typically defines the layers in its constructor. The constructor method, obviously the special method, underscore underscore init underscore underscore, and specifies how data will pass through the network in the forward method. There's a method, and we'll see this once we start creating these models, but there's a method that's very important, the forward method, and we'll be using this a lot when we are constructing our neural networks actually. PyTorch handles much of the complexity behind the scenes, making it straightforward to set up a feed-forward network. And we'll see this. Actually, we'll work with a feed-forward neural network as we continue. We'll create a model using this network. But as you will see once we actually start writing the code and working with these networks, is that they are very, very easy to understand and also easy to follow what's happening. But behind the scenes, there's a lot of things that PyTorch is taking care of, and a lot of mathematics and a lot of movement, but we don't see that. So training a neural network and also to make predictions, it's truly very easy, and once you understand it, you find that it's just something that you can do over and over and over again, just making some adjustments here and there, experimenting with the neural network, and that's going to be very important, the experimentation. That's essentially what you you start training these neural networks. That's what we'll be doing with and trying to see how the neural network performed by looking at the loss function. But once we create the neural network itself and we create a model, you'll find that it's just the same concept over and over and over and over again. So it becomes truly very easy to kind of like work and to train data and also to run predictions. It becomes just a repetitive thing. And that's why I actually wanted us to go to ChatGPT. We can get the code from there because you can memorize the code and how to write it and everything else. But now, especially in this age, I think most of the times it would probably be helpful to just maybe utilize ChatGPT to write for us the code, and then we can be able to either debug and also try to analyze the code and learn that way. And I think that is going to be a very easy way to learn and also a very effective way to learn. I think there's no time of memorizing things. The easiest way is that you just have the chat GPT write the code, and then you can try to debug the code and also analyze the code and also learn from the code. And that's primarily what I want us to be doing as we continue with our journey on learning PyTorch. Uh, and one more thing that I wrote here I wanted to pass along is that feed-forward networks are widely used due to their simplicity and also effectiveness in a vast range of applications. They serve as a foundation for understanding more complex neural network architectures. And that's why I also want us to start with these feed-forward neural networks and also do the recurrent neural networks. And then we will also do the convoluted neural networks as well. We'll work with different neural networks in PyTorch, and this is going to be a gateway for us to get to understanding the basic concepts of our neural networks when we are coding and trying to see how those concepts work. And that is going to give us the basic knowledge essentially that we need when we are learning, building, and experimenting with neural networks. And good simple example that I found on Google for feed-forward neural network is you have an input here, input layer here. You have the input layer. You have input 1, input 2, input 3, input 4, and then it's a feed-forward. Information flows one way or one way. So we have this. See, this is connected to this, and this is connected to this, and this is connected to this, and this is connected to this. But information is flowing forward, feed forward. It's feeding forward. So we have this one, they all feed forward to this, and then this feeds forward to this and feeds forward to that. Then we have our output. But that's the feed forward neural network. I just wanted to show you a basic representation that I found on Google. And then we can go to next, and next we have the capsule networks. And capsule networks are a relatively new architecture that aims to enhance the performance of convolutional neural networks by adding structures called capsules, which better capture spatial hierarchies between features. So capsule networks are a relatively new architecture that aims to enhance the performance of convolutional neural networks by adding structures called capsules, which better capture spatial hierarchies between features. The capsule networks are less commonly seen, but are gaining interest for potential improvements over standard convolutional neural networks. Applications, while still a relatively new area of research compared to more established neural network architectures, capsule networks show promise in areas like image classification. They can classify images while considering spatial hierarchies and transformations. Capsule networks can also be utilized in object detection where they can help with recognizing and localizing multiple objects within an image along with their orientation and pose. And also, capsule networks can also be used with robotic robotic vision in understanding objects in a three-dimensional space, crucial for robots interacting with real-world environments. And another thing I put here to mention to you was that capsule networks, which are often abbreviated as CAPSnets, represent an intriguing development in the field of neural networks introduced by Jeffrey Hinton and his colleagues in 2017. The main innovation of capsule networks is their ability to encode hierarchical relationships between different parts of an object, potentially solving some of the limitations found in traditional convolutional networks. Implementing capsule networks can be more complex and computationally intensive compared to traditional convoluted neural networks, primarily due to the dynamic routing process. This has limited their widespread adoption so far, although ongoing research is addressing these challenges. Despite these challenges, the potential of capsule networks to revolutionize how machines perceive and interpret complex visual information continues to drive interest and exploration in this area. Basic illustration of a capsule network here, and we have an image here. Then we have a convolutional layer 1, convolutional layer 2, 3, and then we have primary caps, and then primary caps reshape, and then finally you have the reconstructed image at the end. But a basic illustration of a capsule network that I wanted to show you for the purposes of introduction to neural networks that we can be able to utilize with PyTorch. And I think that does it for neural networks that we can use in PyTorch. I just wanted to show you a little bit of something here, just a little of illustration about how we work with neural networks in PyTorch. It's just a PyTorch workflow, and this is gonna get us ready as we start to get ourselves into learning how to create neural network through code, and also create a model and train the model and make predictions with the model. But the way we work with PyTorch, the workflow involves, you see number one here, we get the data ready. So you have your data, whether you have the millions and millions of images that we had of the handwritten letters, like letter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and or 1 or 0 to 9, and you have that data handwritten letters 1, 2, 3, 10, and you have thousands and thousands of them, and you want your neural network to be able to tell you whether this is a 1, whether this is a 5, whether this is a 7. Number one thing is that you get that data ready. And most of the time that data is going to come in like it's going to be an image. So you get the data ready, you convert it from an image into a tensor. And this is where we'll be talking about tensors. And I did introduce you a little bit to tensors when we were talking in my previous video. But this is where we actually, because in PyTorch, we are primarily going to be working with tensors. It's going to be tensor, 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 tensor. That's going to be our data. So here we're going to have to convert our images, our data into tensors, and that's how we make it ready, and also convert it to tensors that can be used in PyTorch. Sometimes when we work with making our data ready, we may get this data in images, then we convert those images, we may convert the images into NumPy array, then we need to convert the NumPy array into torch.tensor data type, and so that we can be able to work with it in our neural network. But that's why we stressed that tensors are the bread and butter of machine learning, and we will essentially be working with tensors, and they are very important. So number one, we get our data ready, we convert our data into tensors and into torch.tensors. And then after that, we build or pick a pre-trained model, and we pick a loss function and an optimizer, and also we build a training loop, and we'll see this once we start working, once we start coding. When we go to ChatGPT and we get our code, and then we go to Google Colab and we analyze our code and we run the code, we train the network, we'll be able to see that as we continue. But I think it's going to be very important, and it's going to be very easy to understand. Once we build 1 or 3 or 4 or 5, 6 models, then after that it's going to be very, very easy, and that is going to provide a basic understanding of neural networks. And with that basic understanding, you can be able to, the sky is the limit. You can essentially create anything. You can create a neural network to solve any problem, or if you continue with the journey, you can create you can create essentially anything. That's my point. You can really create the world. You can create the world with neural networks, and we all begin from tensors. That's why it's very important to understand tensors before we even go anywhere else. And the reason I was telling you about tensors and the shapes of tensors, the size of a tensor, the shape of a tensor is also very important. Even when we get the code from ChatGPT, you'll see that that code sometimes is going to have some size or shape mismatch for the tensors, and we'll be able to do a lot of debugging on that as well. But as long as you have a basic understanding of tensors and also a basic understanding of tensor shape, tensor size, then the NumPy arrays that we saw and tensors, torch.tensors, they all work the same. They're pretty much the same. You can do pretty much the same as we saw with NumPy. I did make a video on NumPy in the previous, maybe a few days ago. If you want, you can maybe have a look at that if you have not been able to have a chance to look at it. And then we're going to fit the model, then we're going to evaluate the model, then we're going to improve through experimentation. Experimentation is very important in machine learning, and also when you're working with these neural networks, as you'll see. And if you are satisfied with your model, then you can save and reload the model. But these are essentially the steps that we'll be able to go through. I just found this to be a very good representation of the overview of what we are going to be covering. We get the data ready. This is going to be a very important step, and it's also going to be the step that we'll probably be able to spend a lot of time. And then after that, we can build or pick a pre-trained model to suit your problem, obviously. And then we feed the model to the data and make a prediction. Then evaluate the model. How is it doing? What is the loss function? And then after that, we can improve through experimentations. Maybe we can do more epochs, maybe provide more data, maybe things like that through experimentation. And then once we finish and we are satisfied with our model, we can save and reload the model to use it another day uh, if we need that. But that's the basic. So I just wanted to introduce you to different neural networks that we'll be learning in PyTorch, or rather that we'll be using with PyTorch. And next, as I said, my next video, I want us to start now actually writing the code with the help of ChatGPT, and trying to analyze the code and also try to create a model in Google Colab. Thank you very much. I appreciate it, and I look forward to seeing you in our next video presentation on this PyTorch series. Gracias. Thank you, guys.